Imagine a world where traffic congestion is a thing of the past, where vehicles are ultra-efficient and sustainable. What if we told you that this could be achieved by applying the McGinty equation to vehicle design and infrastructure? Indeed, the idea is as intriguing as it sounds. The transportation system we have today, while quite advanced, is far from perfect. It's plagued by issues like traffic congestion, environmental pollution, and energy inefficiency. Not to mention the infrastructure supporting it is often outdated and unable to keep up with the increasing demand. But what if we could change all that? What if we could revolutionize transportation as we know it? Enter the McGinty equation. This mathematical formula might seem unrelated to transportation at first glance, but it holds the potential to transform our travel experience completely. Now, you might be wondering, how can an equation revolutionize transportation? Well, that's where it gets interesting. The McGinty equation is a unique blend of quantum field theory and fractal mechanics, with a sprinkle of gravitational effects. This equation, in essence, represents the fundamental laws of physics in a novel way. It provides us with a new perspective to not just understand the universe better, but also to apply this understanding in practical ways, like revolutionizing transportation. By applying the principles of the McGinty equation to vehicle design and infrastructure, we could create a transportation system that is not just ultra-efficient, but also sustainable. We could design vehicles that are more aerodynamic, consume less energy, and emit fewer pollutants. We could build infrastructure that is more resilient, adaptable, and capable of handling the ever-increasing traffic demand. This might sound like a science fiction dream, but it's not. The potential is real, and the possibilities are exciting. By leveraging the power of the McGinty equation, we are standing at the precipice of a transportation revolution. To understand how this could work, we first need to delve into what the McGinty equation is. The McGinty equation, in its simplest form, is a mathematical formula that describes the behavior of quantum fields. This equation is a bit like a recipe, with each part serving a specific role to create a whole. Let's break it down. First, we have P squared T, which is the solution of the free quantum field theory. Think of this as the base of our equation, much like flour is the base of a cake. This part of the equation deals with the behavior of particles in a quantum field, without any external forces acting on them. Next, we have Fractal XTD-MQS. This term represents the fractal potential, a self-similar structure that appears throughout the equation. Imagine it as the sugar in our cake, bringing a level of complexity and sweetness to the mix. The fractal potential term VYT has a self-similar fractal structure, which is described by the constant parameters V0, L, and S. This fractal correction term can be derived using integral calculus, Laplace transform, and the convolution theorem. Then we have the modified McGinty equation piece xt equals sign PSQ ft xt plus PES fractal xt dmqs plus PES gravity xrg. This is where things get a bit more interesting. Here, PES gravity xtg represents the perturbative effects of gravity on the quantum field, with g as a parameter that characterizes the strength of the gravitational force. This is akin to adding baking powder to our cake, causing it to rise and giving it more substance. Finally, the modified McGinty equation, combined with general relativity, represents the perturbative effects of gravity on the quantum field. This is like the oven's heat, providing the external force that transforms our raw ingredients into a delicious cake. In essence, the McGinty equation is a mathematical tool that allows us to predict and understand the behavior of quantum fields under various conditions. Now that we understand the McGinty equation, let's see how it can be applied to vehicle design and infrastructure. The McGinty equation is not just a theoretical concept, it has practical applications, particularly in vehicle design. Picture this: vehicles that are not just efficient but ultra-efficient. Vehicles that leave a minimal carbon footprint and contribute to a sustainable future. This isn't just a pipe dream, it's a possibility made tangible by the McGinty equation. Consider the equation's two key components, the free quantum field theory solution and the fractal potential term. The first can be used to predict and control the vehicle's behavior in various conditions, making it more adaptable and efficient. The second, with its self-similar fractal structure, can be used to design intricate yet robust vehicle components that are both lightweight and durable. Moreover, the modified McGinty equation, which incorporates the effects of gravity, can be applied to optimize the vehicle's performance in different gravitational conditions. This could lead to the creation of vehicles that can adapt to various terrains and environments, enhancing their versatility and performance. Imagine a vehicle that can adjust its performance based on the terrain or the gravitational pull, or a vehicle that can optimize its fuel consumption based on the current driving conditions. This is what the McGinty equation can bring to the table in the realm of vehicle design. But the applications of the McGinty equation don't stop at vehicle design. The infrastructure that supports our vehicles can also be revolutionized using the principles of the McGinty equation. Just as it can help us design ultra-efficient vehicles, this equation can also guide us in creating more efficient, sustainable transportation systems. Take traffic flow, for instance. Using the McGinty equation, we can analyze and predict traffic patterns in a more sophisticated way. Think about it. A city's traffic isn't just a bunch of cars moving around. It's a complex system with variables and parameters that change constantly. By applying the McGinty equation, we could potentially reduce congestion, enhance flow, and make our commutes smoother and quicker. Now, let's talk about efficiency. The McGinty equation can help us optimize the use of existing infrastructure. It can guide us in making strategic decisions about where and when to build new roads, bridges, or tunnels. This means fewer wasted resources and more efficient use of what we already have. And then there's sustainability. With the McGinty equation, we can minimize the environmental impact of transportation infrastructure. It could help us design systems that reduce carbon emissions, promote the use of renewable energy, and are more resilient to the effects of climate change. So, what does this all mean for the future of transportation? The application of the McGinty equation to transportation presents a fascinating and promising future. With this equation, we can imagine ultra-efficient vehicles, designed using quantum field theory and fractal mechanics. Not only that, but our infrastructure can be reimagined, taking into account the perturbative effects of gravity. This blend of science and practical application has the potential to dramatically improve how we travel, making journeys quicker, smoother, and more sustainable. The future of transportation could very well be shaped by the McGinty equation, revolutionizing the way we travel and making our world a more efficient and sustainable place.